Have you ever built a regression model that fits your training data absolutely perfectly, only to watch it completely bomb on new data? Yeah, we've all been there. Sometimes your model is simply trying way too hard.
You get this amazing training fit, but terrible generalization. It's the classic trap of overfitting. And honestly, it's exactly the core pain point we're going to solve today.
Okay, let's dive right into this. Enter ridge regression. It's basically a regularized version of your standard linear regression. What it does is add an L2 penalty to the mix, which actively discourages those massive overgrown coefficients. Adding that L2 penalty essentially forces your coefficients to stay small. And why do we care? Well, smaller coefficients directly drive down the variance. That drastically improves how our model is going to generalize to new unseen data out in the real world. Let's look under the hood at the ridge cost function. You'll see it has two main parts. That first term right there, that's the MSE, which is just doing its normal job of minimizing our prediction error. So it breaks down super logically. The MSE portion is basically screaming, fit the data, while that second part, the penalty term, is whispering, keep the weights small. Oh, and one absolutely crucial detail here. The intercept, theta 0, is left totally alone. It doesn't get regularized. And this brilliantly illustrates how we tune that penalty. Alpha is the dial that controls the strength of the regularization. If it's set to 0, you just have ordinary linear regression. But as you turn it up, you hit a nicely balanced state. Crank it too high, though, and you're dealing with a very large alpha that completely risks underfitting the data. So as alpha increases, your coefficients shrink and your variance drops, but your bias goes up. It's a classic trade-off. Remember, the ultimate goal here is finding that perfect balance, not just picking the absolute largest alpha value you can find. Now, how do we actually calculate those optimal weights? Ridge can be trained in two different ways. You can either compute them directly using a closed-form solution, or you can update them iteratively, step-by-step using gradient descent. So what does this all mean for us? And where does Ridge really shine? Well, it works incredibly well when your predictors are highly correlated, or when you're dealing with complex polynomial or high-dimensional data. It's also your go-to when all the features simply have to remain in the model because it handles multicollinearity like an absolute champ. To wrap up this explainer, if there's one golden rule to take away, it's this: ridge regression controls model complexity. The mantra is literally, don't fit harder, generalize better. By keeping those coefficients smaller, you get lower variance, greater stability, and ultimately much better generalization on fresh data.